like I said, we finished with number 6 last time. Number 6 is unique, and I'd kind of like to continue with this pattern here. With number 6, whenever you have an integrand that is a product, you're always going to have some kind of an issue that you're going to have to deal with. And of course, number 6, you can see pretty clearly that it is a product. It's sine of x times cosine of x. Where we ran into an issue last time is there was no obvious composite part of the product. There was no like obvious function within a function. And so this is where we kind of artificially did this to make this work. So my suggestion was that we think of sine of x as sine of x to the first, in parentheses, times cosine of x dx. And that might seem like a really simplistic, unnecessary thing to do, but it actually sets us up really nicely, because now what we can do is we can look at sine of x and say, well, that's kind of the inside of the composite. And we can look at the 1 up there and say, well, that's sort of the outside of the composite, and proceed from there. So if we do it this way, we'd say, all right, well, the inside is sine. What's the derivative of that inside? Cosine, and that's the other factor, right? So Timmy didn't mess up. He did this just right. So what's going to happen here is we find our antiderivative. We are going to antidifferentiate the outside function. So the way that you antidifferentiate the first power is you use that power rule. So this would end up being sine of x, quantity squared, over x, and then, not over x, over 2, sorry, and then plus c. And of course, this is the point where people, I think, legitimately will ask, okay, I get the whole squared and the over 2 thing, that's okay. Where on earth did the cosine go, right? That cosine was there, and all of a sudden it's just gone. Where did it go? Back inside the boxes, right? It went back inside the bigger box. The way that you could test this out, of course, you could check your answer by doing a derivative, and if you did, you'd see that you end up with the exact same integrand that you started with. You could have done this the other way. If you did it the other way, you'd ended up having to do some minus sign adjusting. I would personally avoid that, just because it's easy to lose minus signs, but that would have worked too for this one. Okay. One last comment here. You can see it there highlighted. If Timmy messes up, too bad. If he makes too big of a mistake, then it's unfixable. So an example would be number 7. You look at number 7, and we'll practice this here just to reinforce a little bit. Can you see how number 7, the integrand is a composite? It's like a function within a function. What's the inside of the composite?
X squared.
It's x squared. And so if you're going to do this whole Timmy messed up the chain rule trick, you'd say, all right, cool. The inside is x squared. What's the derivative of the inside? 2x. And so in order for this to work, the other factor in the integrand has to be 2x. And so we look over here, and we look over here, and we don't see a 2x anywhere, right? So if we were only off by a factor of 2, that's not a big deal. We can fix that, right? We just go times 2 times 1/2 like we did last time. But the fact that Timmy is off by not just a 2, but also an x, the x is what makes this completely the wrong form. And it's not that this doesn't have an antiderivative. It's just that this method won't work, okay? And so it's very possible that this does have an antiderivative. I'm sure it probably does, but we don't know what it is, and all the methods we learn in this class are not going to cover that. And so what you can't do is you can't say, hey, let's just multiply by 2x and divide by 2x and we're good. That doesn't work. It just means it's a whole different form. So please don't say, hey, cool, I'm only off by an x, let me fix that. If you're off by an x, something's wrong. You need to rethink what you're doing, okay? Question?
So if we got that on like a quiz or a test, how would you like us to answer?
So this is a little bit of foreshadowing. So I wouldn't give you something like this.
Okay.
Because it's not that this doesn't have an answer. It probably does. It's just beyond us. What I'm foreshadowing a little something. When we get to chapter 5, there's going to be various fraction forms and like little details. Like I'll give you an example. In chapter 5, you'll see something like this, where it's 1 over x squared plus 1 dx versus x over x squared plus 1 dx. And these are 2 totally different forms. I mean, honestly, they're only different by an x. And if you looked at the top one and you said, hey, we're only off by like a 2x factor, then that's going to lead you down a wrong road. Whereas if you looked at the top and you're like, whoa, okay, yeah, there's no fixing that I can do. I need to rethink what format I'm going down, what pattern I'm looking for. The truth is, the one on the top ends up being leading to arctangent, and the one on the bottom leads to natural log. And when we get to chapter 5, we'll deal with like how do you identify which one is which, and it's not that hard to do. We just haven't done it yet. But if you get mixed up and you think, hey, well, I could just multiply top and bottom by an x and I'm good, now all of a sudden all these forms get all messed up. So I'm foreshadowing a little bit. So don't worry too much about number 7. Okay, any other questions? Okay, let's go ahead and move on then. Let's move on to this process that I've been talking about. This process is called, it's got 2 names. Some people will call it change of variables. Other people will call it U substitution or just substitution in general. There's no God-given reason that we use the letter U, just whatever, just what we use. So change of variable, U substitution really are the same thing. So I'll kind of use those terminologies interchangeably. And so let's take a look here at a few examples. And these, a lot of these examples would be ones where you could, you really could use Timmy messed up the chain rule. In fact, I would say number 1, if I were doing a quiz or a test or doing something and I came across number 1, I'd do the Timmy messed up the chain rule pattern. I'd be done pretty quick. You could also do U substitution. So I thought I'd show you U substitution with a more easy one. We'll do a couple of easier ones like this, and we'll get into some ones where U substitution I think is definitely the better method. Okay, so this is just a more organized approach. If you're a step-by-step person, this might go a little bit better for you. Okay, so here we go. We've got the antiderivative of the square root of 2x minus 1. Big hint here that we want to always think about is when we're setting up our substitution, we want to make the inside function, as you identify the composite stuff, I want to make the inside function, bless you, your u. So let's identify it. Do you guys see in number 1, what is the inside part of the composite? 2x, yeah, 2x minus 1 is the inside part. So off to the side here, I'm going to make that my u. So u equals 2x minus 1. Whenever you set up a u, you're also going to want to find your du. And so maybe, let me do a little, I'll do an in-between step here. It's the differential. This might be helpful. If I did the derivative, I'd do du dx. And what is du dx equal to? It's just a 2, right? And so what I'm going to automatically do is I'm going to automatically multiply that dx over to get a differential. So it'd be du equals 2 times dx. So I don't think I'll frequently show that step. I'll just mentally multiply the dx over. Okay, so the key here is finding the u, making the u the inside, and then finding the du. Now what we can do is use that information and kind of go back to our integrand and do some substituting. So check this out. I'll do this in stages. I think ultimately we don't want to do this in stages because we can do it quicker. But I'm going to say, okay, 2x minus 1 is my u. I'm going to write this as u to the 1/2 dx. Does that part make sense? Obviously, the square root is the to the 1/2 part, and I've set my u equal to 2x minus 1. So I'll just replace the 2x minus 1 with a u, because they're equal to each other. I'm allowed to do that, and u to the 1/2 dx. So if we're honest about this, I have not completely substituted yet, right? Because I've got a u and an x in my integrand. I want to complete the substitution. I want to get rid of the dx. Does anybody see what I could put in place of the dx? Like what's equal to dx? Not just du, du over 2, right? So if I come back over here to the box, I could say, well, if I divide by 2, I get du over 2 is equal to dx. So that old principle of substitution you guys learned way back in Algebra 1, if two things are equal to each other, you can replace one with the other. And so I can replace the dx with du over 2. So this gives me u to the 1/2 times du over 2. And it's at this point, of course, we can look at it and say we started off with everything in terms of x. Now at this point, we have everything in terms of u. And so I think we should feel free to proceed from here. Make sense? So a couple things here as far as just efficiency stuff. If I was doing a quiz or test or something and trying to be efficient with my time, I don't know that I would ever show that step. If you're kind of beginning, here and you want to show stuff like that, it's no problem at all. But don't feel like you have to show that step. If you can see the substitution and just go boom, boom, do it in one step, no problem. But make sure you do show that substitution. And then one other thing real quick, Jake, and I'll get your question. One thing that I would probably do automatically is, do you guys see this over 2? Isn't that just a constant multiple? And with an integrand, you can take constant multiples out of the integrand, right? Put them out front. So I think before I did anything else, I would write this as 1/2 integral of u to the 1/2 du. And it's at this point we could do a pretty quick and easy power rule, and we'll get there in a second. Jake, your question.
So we don't have to show the du dx equals 2, but do we have to show the du over 2 equals?
I'm okay, and I'm totally okay if you can just like divide by 2 mentally and
Okay.
slide it in there to substitute. No problem.
Okay.
No problem at all. Any other questions? You see how we've made this simpler, right? Instead of a 2x minus 1 in a square root, we just have square root of u. Just made it a little bit easier. This one might seem a little trivial. Later on, it's not going to seem so trivial. It's going to be like, whoa, substitution really helped. Made it a lot easier. Okay, so 1/2, that would be u to the 3/2, and then divided by 3/2 would be times 2/3. Your plus c really should be there right now because you just completed your antiderivative. And then our final step would then be to plug back in what our u was to begin with. So the 2's cancel out. We end up with 1/3. U is the same thing as 2x minus 1, so I'm just going to plug back in for that to the 3/2 plus c. And I'm done. You should, of course, be able to take that antiderivative, differentiate it, and get what you started with as a check if you so chose. Comments or questions?
Mr. Anderson, where'd the 1/2 out front go?
The 2's canceled. You could, of course, write it as 2/6 if you wanted to. No problem there. Remember back in like 8th grade math, like reducing fractions was like, you better do it or you're going to get an F or whatever. Like we relax that a little bit. So don't stress. Okay. Anybody else? Okay, fair enough. Full disclosure, number 2 is a little tougher. I want you guys to try to get the substitution. I'm absolutely convinced that some of you definitely are going to see it. Some of you might not, and that's okay. Just know that number 2 is a little bit tougher. See if you can get it substituted and proceed. Just be aware it's a little tougher. So it might require a little more thought, but you guys are smart, so you're going to do fine. Check it out. Give you a couple minutes to do it. Saw a lot of good work. Just peeking over shoulders and talking to you guys. A lot of good work out there for sure. So you'd want to still set up your u to be the inside function, just like we did with the previous one. And anytime you set up a u substitution, you're going to want to do the derivative of that, find the differential in this case, du equals 2 dx. And this is kind of our jumping off point. At this point, it looks just like the other one, doesn't it? But you do have that extra factor of x we need to deal with. So this would look like this. Integral of x, then you get u to the 1/2. And then here's what I usually do. Feel free to do this if you want. If I was going to replace the dx with du over 2, I usually just do this, du over 2. Makes sense? Just do it in one step. If you see it, do it. If you want to do it in 2 steps, obviously that's no issue. You could do that. At this point, the substitution is almost done, but there's one last pretty significant hurdle to clear, and that is, what do we do with that? Yeah, we go back and we solve for x. Guys, listen, peeking over shoulders, watching you guys do your thing, a really high percentage of you saw what I'm about to do, and that's really encouraging. So keep working together and talking these things through and doing the good work you're doing. I can just add 1 to both sides and divide by 2 and get u plus 1 over 2 is equal to x. Going back to the box right there. And remember, anytime something is equal to something else, you can replace something with something else. Right? You can substitute. That makes sense? If something equals something else, you can replace that something with that something else. So I'm going to go back over here. I'm going to replace the x with what I know it's equal to. I'm going to replace the x with parentheses u plus 1 over 2. And I still have the u to the 1/2, and I still have the du. Walking around, saw a few folks that got to about this step, and maybe you just ran a little short on time or whatever. But this is a good substitution step. At this point, we're totally substituted. All of the x's have been turned into u's. And save for a little bit of algebra, we're just about ready to proceed with an antiderivative. Question?
Why is it du over du over 2?
So I took on this step right here, the du over 2 is right here. I just kind of, in my head, automatically pulled the over 2 out as a 1/2. Does that make sense? You don't have to do it that way. If you want to leave it in there and then later on get it out, that's fine. But I would not leave it in there. At some point, I would get it out of there just to make it easier on yourself. Make sense? Okay. Good question. And to be honest, Jake, I'm about to do something real similar right now. To simplify this, do you guys see how that's just another 1/2? That 2? Like the over 2 is just another factor of 1/2. I'm going to pull that out. It's going to be 1/4 integral of u plus 1 times u to the 1/2 du. I really hope you're paying attention. I have seen questions like this in some form or another show up on a quiz, show up on a test, and I've also seen a lot of people get to this point right here. Do a lot of good work with substitution. They do all that stuff on the right side correctly, and they get to this point, and then they make a major mistake. You know what that major mistake is? They just anti-differentiate right here, and I want you to remember this. If your integrand is a product, you still have a significant issue, right? If your integrand is a product, it's simply not going to work unless it's a Timmy nicely messed up the chain rule thing, and he didn't. So how do I take this integrand, which is a product, and turn it into something that is not a product? What do I do, Jack? Yeah, multiply it out. Do a distributive property. Yeah, exactly. So I'm going to distribute into here and here. That'll give me 1/4 integral u to the 3/2 plus u to the 1/2 du. So if we do that algebra correctly, we'll be in pretty good shape. And you have to do that. That's not an option. Now it's not a product, right? It's just a term plus another term for an integrand. We could just go term by term and do the power rule twice and be done. So here we go. I'll come up here. So when I do that, I end up with 1/4 times 2/5 u to the 5/2 plus 2/3 u to the 3/2. Sorry, I kind of ran out of room there. And then my final step would be to plug back the 2x minus 1 back in for u. And I suppose, is it okay if I distribute the 1/4 at the same time? Okay. So 2/20 is really 1/10. So you get 1/10 2x minus 1 to the 5/2. 1/4 times 2/3 is 2/12, which is 1/6. And again, I plug back in. And I don't want to forget my plus c, which I did forget. Oh my goodness. That hasn't happened in a while. I put my plus c back in up there. It's in red. Okay. Okay, what do you think? That was a little more challenging, wasn't it? That's also a case where use substitution really is kind of, you have to do it. You don't really have a choice. Timmy messed up the chain rule. Too bad there. You're going to have to use substitution. Okay. Any questions? Okay, let's move on to number 3 then. I want to do number 3 with you. So, with number 3,
That's beautiful.
it is beautiful, I agree. With number 3, if you look at this carefully, I want you to notice the commonalities with what we've done so far. So if you were just to approach this on a quiz test, homework assignment, whatever, you'd look at this, and wouldn't maybe the first thing you notice possibly be my integrand is a product? That would be maybe one thing you'd notice first. What would be another thing you'd notice? Pretty significant. You got some composite stuff going on. And doesn't the composite stuff, hasn't it been ramped up a little bit? Let me do a quick rewrite here just to show you how much it has been ramped up. The first factor in there, sine squared of 3x, really could be rewritten like this. And I would suggest this. Sine of 3x, quantity squared, and then cosine of 3x dx. So if you were to look at this, and say, hey, it's a product. I see it's something times something. And see that there's composite stuff going on. Do you see how the composite is a little more kind of woven together? There's a little more to it. Because if you were to stop here and say, all right, what's the inside function? Can you see how there might be multiple answers to that question? If I were to say, what is the inside function, what would you say?
3x.
3x is a pretty obvious answer, right? And that's right. 3x is definitely an inside function. And as a matter of fact, isn't it an inside function in two different spots? Right? It's cosine of 3x, right? And then it's sine of 3x. And if you were to say, hey, let's make the u 3x, it would eventually work. But there's an easier way. Because isn't there another inside function? What is it? Sine. Yeah, exactly. So I would look at this over here on the left, and I would say that, to use the terminology I've used in the past, isn't that like a box within a box, and then that's within a whole other box? Do you see how there's 3 boxes on that purple factor? How many boxes are on the unboxed factor? It's like 2, right? There's cosine is the big one, and 3x is the little one. So guys, I want to give you a principle here. If you ever have a situation like this where you ever have a box within a box within a box, or a function within a function that's within this whole other function, your easiest route is going to be to make the middle or the medium-sized box your u. You can definitely make the tiny box, in this case the tiny box is 3x, you can definitely make that your u and it'll work. But I think the easier of the ways is to make your middle-sized box your u. So your middle-sized box is sine of 3x. And this is where I think you're going to realize that the substitution thing has the potential to really simplify stuff. So I would do this. I would say u equals sine of 3x. That's my middle-sized box. That's going to make this a lot easier. If that's the case, what would du, as you do your derivative, what would du be? That's right, 3 cosine of 3x. And then don't forget the dx gets multiplied over. 3 cosine of 3x dx. And here's where this makes stuff that's about to come up a whole lot easier. Check out your substitution. Can't you replace this whole inside, this whole sine of 3x? You can replace that with simply a u, right? So that's what I'm going to do. I'm going to say u squared. And then just for illustrative purposes, I'm going to leave the cosine of 3x in there. But what I want to do here is I want to substitute the dx out. So what can I replace the dx with? Yeah, du over that whole thing, right? Because you can just divide both sides here by 3 cosine of 3x. And you end up with dx equals du over 3 cosine of 3x. So I can replace dx with that. Bless you. du over 3 cosine of 3x. And of course, major cancellations happen. Yay, this is going to look really simple here in a second. Isn't that over 3 just a 1/3? So I'm going to get that out of there. So it's 1/3 integral of u squared du. And of course, it's at this point that I would ask you to consider how much simpler what we have up there looks as compared to what we started with. U substitution has really helped this. You could certainly do number 3 with the whole Timmy messed up the chain rule pattern thing. You could definitely do that. And if you can, more power to you. I'm not going to stop you. It's good. It works. But if you look at this, a little more complicated, and U substitution really simplifies this. Makes it a lot easier looking for sure. Okay, so to finish this out, all we have to really do is find the antiderivative of u squared. It's a power rule. So I'm going to write this as 1/3 times 1/3 u cubed plus c. And my final step would be to plug back in. So it would be 1/9 times sine cubed of 3x plus c. And again, if you have any doubts, you can just find the derivative and check it out. Should match the integral. Oops. Okay, do you guys have any questions at all? I think we'll skip number 4, maybe leave it as a warm-up for the next time that I see you guys. I guess that's tomorrow. So if you would, let's jump forward a little bit. Oh, come on.
Oh, it's Monday.
All right. So, up to this point, the only thing we've looked at is indefinite integrals, the stuff with the plus c on the end. It's at this point we're going to transition and we're going to do 2 examples where you can do the same kind of activities we've been doing, except do this with definite integrals, where you got the limits of integration, integral from such and such to such and such. Like the first one is integral from 0 to 1, and so all this same stuff applies. There is one little twist to it we'll get to, but we'll look at a couple of definite integral concepts here, and that will kind of wrap things up at that point, at least for 4.5. All right, so take a look at number 1 here. Number 1 says use change of variables, also known as U substitution or just substitution, to evaluate. Let's just get a quick look at it here. Looking at the integrand, do you all see how the integrand is a product as something times something? Do you see how also one of the factors is composite? This is that pattern we want to see. We've looked at this pattern between last time and today, I think 5 or 6 times at this point. So if you would, let's take a look at what the U should be, and we'll get to the du and that new limit, new low and new high limits. The U should always be which part? The inside. And what's the inside on this one? X squared plus 1. Okay, so then to get our du, we just need to find the derivative and multiply the dx over. So in this case, du would equal what? 2x dx. That's right. So I'm going to be really careful with this. And I want to emphasize something for you guys. As you look over here at the integrand, do you see how everything is in terms of x? And isn't our goal in the end to get everything in terms of u? So I want to point a couple things out. This is obvious. This is obviously in terms of x. I hope that you're watching. There's going to be a little transition up here that's pretty important. That's obviously in terms of x. And that's obviously in terms of x. That's obviously in terms of x. But what about those? What are those in terms of? Are they just generic, or are they y's or something, or 0 and the 1? Are they in terms of x also, or is it something else? Think back to what a definite integral is. It's an infinite sum. Sorry? Yeah. It's how do the limits play into the whole infinite sum area thing, right? How do limits play into that? They're x values, and what are the x values bounding? It's like from 0 to 1, right?
Yeah.
So those are the boundaries for. Think of the graph. But what about the graph of the function? The base for the areas, right? Aren't the 0 and the 1 kind of the boundaries, like where you start calculating area and where you stop? Mm-hmm. So if you were to look at this on a graph, I'm going to erase all this, so please don't write this down. This would be, this would be like some seventh degree function. Who knows what it looks like? Let's say that it does something like this. Wouldn't the integral from 0 to 1 essentially be saying, let's find the area from x equals 0 to x equals 1? That make sense? So do you see how the 0 and the 1 are actually in terms of x? That's a really important thing for us to notice, because up to this point, we've been able to pretty clearly see, hey, I've got this, u substituted in here and another u substituted in there, but there's an x left over. It's really easy to forget that the 0 and the 1 are also in terms of x. And so when it comes time to substitute, we're going to need to substitute for those as well. Does that make sense? Okay. Let me erase all this stuff and we'll get to it. So we already set up our substitution there on the right. So let me keep rolling with this. I'm going to write integral. I'm going to leave off the 0 and the 1 because I'm transitioning over to u's, and I'll fill those in here in a second. I know that u equals x squared plus 1, so it would be u cubed. That x is still hanging out there. What could I replace the dx with? You starting to see that pattern, right? We always divide that stuff over. That's exactly right. So du over 2x. Notice I didn't put the 0 and the 1 limits in there yet. I'm just going to leave those off for the moment because I know those are in terms of x. I want to get rid of those. Do you guys see how the x and the x cancel out? So I end up with integral of u cubed du, and then I'm going to go ahead and take that over 2, take it out, like we did on the previous question. So it's at this point, I'm finally going to deal with those limits. So I've got a low limit of x equals 0 and a high limit of x equals 1. Does anybody have any ideas about how I could transform those x's for the 0 and the 1 into u's to get my new low limit and my new high limit? Any ideas? Yeah. Why not just use the equation that we used to substitute, right? U equals x squared plus 1. So for the new low limit, be u equals, well, the old one was 0, so it'd be 0 squared plus 1. And of course, 0 squared plus 1 is 1. And the new high limit would be u equals 1 squared plus 1, and 1 squared plus 1 is 2. Okay, any questions? So it's at this point, everything is in terms of u's, right? The integrand, the limits, everything is in terms of u's. Because this is a definite integral, we are not going to go back to x's. We're just going to leave everything in terms of u's, and the number that we get with the u's would be the exact same number we'd get with the x's. So with these definite integrals, don't be tempted to plug back in with the x squared plus 1. We're just going to go with u's from here on out. So the way this would work, the way this would finish, we'd find our antiderivative would be 1/2 times 1/4 u to the 4th, evaluated from 1 to 2. We're just going to do that FTC1 thing. So this ends up being, let's see here, 1/8 times 2 to the 4th minus 1/8 times 1 to the 4th. Let's see here. 2 to the 4th is 16. 1/8 of 16 is 2. So I'm getting 2 minus 1/8. So 15/8. Yeah. 15/8. Not the prettiest of numbers, but whatever. It worked. Okay. So do you see how I never plugged back the x squared plus 1? I never plugged that back in, right? Because I converted everything over to u's, I can just stay with them because it's a definite integral. And if you remember, with an indefinite integral, don't you always get the blah, blah, blah function plus c? But with a definite integral, what do you always get? A number, right? And so this 15/8, if I would have stayed with the x's, we could have done this one with Timmy messed up the chain rule. This would actually have been a pretty easy one to do, right? If you look at the inside, what's the derivative of the inside? 2x. And so the other factor needs to be 2x. Isn't he off by just a factor of 2? So you could have left everything in terms of x's, and this one would have worked just fine with that, and you should have gotten 15/8 doing that method, just like we did with the u's. So you could have done this either way, and if you feel like it later on, go do it the other way and make sure that it actually is the same answer. Okay, do you guys have any questions? Yeah, Johnny.
So you change from 2 to 1 whenever you form an integral because you switch to u?
So and when you say the 2 and the 1, you're talking about this?
Yeah.
Yep, so the old limits, the 0 and the 1, those were in terms of x. And so in order for this to work, I needed to change those over to u's as well. And so, yeah, so I just used my u equation, my u in terms of x, to get those over to u's. Did I answer your question? Yep. Okay. Anybody else? All right. Take a look at this one. This is number 2. This is, I think this is, at least on every set of multiple choice questions I've seen in recent memory, this sort of question has appeared. Yeah. So it says, which of the following options is equivalent to that indefinite integral? So can you see what they've done as you start to look at those options? Can you see how they have completed the substitution, but they didn't actually finish and evaluate it? So they're wanting you to match up the correct substitution. This is basically assessing, do you know how to substitute and get everything set up in the appropriate places? So take a look here at number 2. Discuss as needed. See if you can figure out A, B, C, or D. Which one goes with what you've got up there? And by the way, that one that we skipped, I think it was number 4 in the previous section, we'll probably just warm up with that one next time. My suggestion to you,
That's freshman initiation, bro.
especially if you don't see it right away,
Or like,
would be to actually try to complete the substitution. So you want to always make your u equal to which part of the integrand? The inside, yeah. So in this case, the inside is x cubed minus 1. That means your du is equal to 3x squared dx. So then as I take this down here and try to substitute, I get integral of u to the 7th times x squared times du over 3x squared when I do that when I do the division like we've done in the past. Thankfully, the x squareds cancel out. That means we've got the right form here. And you end up, of course, with 1/3 integral u to the 7th du. And this is where, of course, we can eliminate d and a, because both of those lack the 1/3. But then it comes down to those limits of integration. Obviously, with b and c, they're different. Can you guys see how in b, the limits of integration have remained the same? They're 1 and 2 still. And remember that 1 and 2 is in terms of x. So really by process of elimination, you could maybe make an educated guess, possibly, and think that it's c, but it's possible for the limits to really remain the same in spite of the process. You know, you'd think that they would have to change. Sometimes they do, sometimes they don't. You'd want to confirm this. So I would run the 1 and the 2 through your substitution, come down here and say, my old low limit was 1, so u would equal 1 cubed minus 1, and that's 0. And I think that would do it for you right there, wouldn't it? You'd be able to say, well, hey, the low limit is 0, therefore it's got to be c for an answer. You guys get c? Okay, cool. I got 1 minute left. Let me make sure you guys remember something. Or I don't know if you will or won't. Do you guys remember anything about even and odd functions? Even and odd. So let's just do 2 quick fill in the blanks. And then we'll just get ourselves ready for tomorrow. Even functions are symmetric with respect to what? It wouldn't be a function if it was symmetric with respect to the x-axis. Y-axis. Even function symmetric with respect to the y-axis. That's one thing I want to make sure you remember. And then odd functions are symmetric with respect to, I think I heard you guys say it, yeah, the origin is right. So tomorrow, hey, please don't mentally check out yet. Tomorrow, we'll look at those. Tomorrow also, it's very likely we'll get into chapter 5. 4.6 is quick. It'll be done in like 10 minutes. So if you would, please bring chapter 5 notes because we'll likely get into those tomorrow. So have a wonderful day. See you tomorrow. Glad you're back for real.